What specific problem does your method aim to solve regarding reasoning capabilities in LLMs, and how does it relate to the contamination issue of benchmark data?
Our method aims to address the problem of understanding how large language models, LLMs, learn to reason from pre-training data, particularly in the context of the contamination issue where benchmark data often overlaps with the training data. We investigate whether LLMs are merely retrieving answers from previously seen data or employing a more robust generalization strategy. The contamination issue complicates the evaluation of reasoning capabilities, as it raises questions about the authenticity of benchmark performance when models may rely on familiar data. By focusing on the influence of specific pre-training documents on reasoning outputs, we aim to clarify the nature of LLM reasoning and determine if it is genuinely procedural or simply a result of data retrieval. This approach allows us to differentiate between effective reasoning strategies and potential overfitting to contaminated data, thereby providing insights into improving LLM training and evaluation methodologies.
How does the proposed method work? Illustrate step by step how you compute the influence of pre-training documents on reasoning outputs.
The proposed method computes the influence of pre-training documents on reasoning outputs using EK-FAC influence functions adapted for large-scale transformers. First, a pre-trained model is established parameterized by theta caret u, which generates completions based on prompts. Next, the influence of a specific training document, x_j, on the model's output is estimated by removing x_j from the training set, retraining the model, and comparing the resulting parameters to the original model. Since this direct computation is intractable, the method employs a Taylor expansion to approximate how the model's parameters change with the influence of document x_j. Finally, the influence score is calculated, which indicates the change in log probability of the completion given the prompt, allowing for a ranking of documents based on their influence on reasoning outputs.
Can you provide a simple yet illustrative example of how your proposed algorithm operates, particularly in the context of one of the mathematical reasoning tasks you explored?
In our study, we investigated how large language models, LLMs, utilize pre-training data to perform mathematical reasoning tasks, specifically focusing on calculating slopes. For instance, when tasked with finding the slope between 2 points, the model retrieves procedural knowledge from influential documents that contain similar reasoning processes. Our algorithm computes the influence of these documents on the model's output by ranking them based on their contribution to the likelihood of the correct answer. In this case, documents that provide step-by-step instructions or code for calculating slopes are identified as highly influential. This demonstrates that the model generalizes from a broader set of documents, applying learned procedures rather than merely retrieving specific answers from its training data.
What are the theoretical or practical benefits of using your method over existing alternatives, particularly in terms of efficiency and generalization strategies for reasoning tasks?
The method presented in this work offers significant theoretical and practical benefits over existing alternatives, particularly in terms of efficiency and generalization strategies for reasoning tasks. By employing EK-FAC influence functions, we can effectively estimate the influence of pre-training documents on model completions without the computational intractability of retraining models after document removal. This allows for a more scalable analysis of how LLMs utilize procedural knowledge across diverse reasoning tasks, as evidenced by our findings that models rely less on individual documents and generalize from a broader set of documents for reasoning compared to factual retrieval. Additionally, our results indicate that focusing on high-quality data that demonstrates procedures can enhance reasoning capabilities, suggesting a more efficient pre-training strategy that does not require exhaustive coverage of every possible case. Overall, this approach not only improves understanding of LLM reasoning, but also informs future data selection efforts to optimize model performance.
How did you validate or test your method? Please elaborate on the experimental design, the datasets used, and the metrics for performance evaluation.
To validate our method, we designed experiments using a query set comprising 80 questions, split evenly between 40 reasoning and 40 factual questions. The reasoning questions focused on mathematical tasks, including two-step arithmetic, slope calculations, and solving linear equations, while the factual questions were curated to ensure a balanced mix of correct and incorrect answers. We utilized a dataset of 5 million documents, approximately 2.5 billion tokens, sampled from the pre-training data of two models, 7B and 35B, to compute influence scores for each document in relation to the generated completions. Performance evaluation was based on the influence scores, which ranked documents from most to least influential, allowing us to analyze the correlation of document influence across similar reasoning tasks and the frequency of answers appearing in the top influential documents for both reasoning and factual queries. Additionally, we conducted qualitative analyses to further characterize the relationship between influential documents and reasoning queries, confirming the procedural knowledge's role in reasoning tasks.
What were the significant results achieved through your method, especially in comparing reasoning and factual question performance, and how do they illustrate your main findings?
The significant results achieved through our method highlight a clear distinction between how LLMs handle reasoning versus factual questions. Firstly, we found that the models rely less on individual documents for reasoning questions compared to factual questions, indicating a more generalized approach to reasoning that draws from a broader set of documents, finding 2. Additionally, while the answers to factual questions frequently appeared in the top influential documents, 55% for the 7B model and 30% for the 35B model, the answers to reasoning questions were almost never found in these top documents, finding 3. This suggests that reasoning relies on procedural knowledge rather than direct retrieval of specific answers, as influential documents for reasoning often contained step-by-step reasoning or code implementations, finding 4. Overall, these findings illustrate that LLMs employ a generalization strategy for reasoning that is fundamentally different from the retrieval-based approach used for factual questions, emphasizing the importance of procedural knowledge in reasoning tasks.